So for any model that we can write the below VC generalization bound in this formula, where essentially the difference between E and E out, so E out is bounded by this bound. Okay? And by this bound, I mean, so this is in sample error that we know that the outer sample error is within this region with high probability. Right? Now, so the larger this number is, the higher the bound, the larger the bound. The smaller this number is, the smaller the bound. Now, obviously, the smaller the better. The smaller means that we can, from E-in, we can accurately believe where our E out is. Now, if the bound is large, then even if we can always calculate E-in, but we have no idea, we have less idea about where E out is, right? So this bound is really important. What we want to do in data analysis, in choosing a model specifically, is that we want to find a hypothesis, the best hypothesis, G, such that we want the E out G to be 0. Right? We want this to be 0 as much as possible. In order to do that, we need to do two things. Right? One thing is we want our E-in to be as close to 0 as possible. So if this is equal to 0, or very close to 0, then that's very good, right? That's the first step. The second step is we really want a very tight bound. So we want the bound to be something like this, so that we know that our E out, so if E-in is close to 0, then we know that E out is also close to 0. Now, unfortunately, these two goals are often contradictory to each other, right? Now, if we choose a more complex model, then we can drive E into 0 more easily. So the more complicated the model is, the more easily you can fit all the observed data, right? So the E-in has more, it's easier for E-in to go to 0. However, if we choose a very complicated model, then the VC dimension become really large. If the VC dimension become really large, then this number become larger, which means that we have a much looser bound. So even if E-in becomes close to 0, we have no idea where E out is. Right? So E out could be very different from the E. So we do not achieve this goal. Okay? Now, on the other hand, if we choose a simple model, then VC dimension is small, so this bound is tight. Okay? So the bound is very tight if we use a simpler model, but it's harder to get E-in close to 0. E-in may be very large, right? Okay? Then we also do not achieve our goal. So we have this trade-off. As we go from simple model to more complicated model, we are increasing the VC dimension so that bound become looser, but we have better probability, we have better chance of getting E into 0. So we have this trade-off there, and this U-type curve is what you will see everywhere in data science, right? This U-shaped curve is almost universal in our applications, meaning that as we increase model complexity, that something goes up and something goes down. What is going down is the E-in, right? In sample error. What goes up is the bound, right? Or the model complexity, if we will. And there's the trade-off. So if we add them together, then this is the true out of sample error, or this is the true E out. And our goal is to achieve the minimum E out, so bring E out as close to 0 as possible. And to do that, we need to find the model complexity, the certain model, such that it actually achieve the perfect, not the perfect, but achieve the best balance between these two countervailing forces, so that we find the optimal point here. Right? So that's in the gist, that's how we do model selection. And we'll talk a lot about them in our course following this lecture. Okay, so that's the idea between approximation generalization trade-off. The bias variance trade-off is very similar. It's the same story, and you can see that it leads to basically the same graph where you have the U-shaped curve again, and our goal is choosing the optimal point here. Okay, all right. So, like I said last time, that so far what we have been doing is we have assumed y equal to fx. We have assumed y equal to fx, and our goal is to find an h that comes as close to f as possible, right? So we want an hx, that's our hypothesis, and I want this hx to be as close to fx as possible. Now, the way we measure how close they are, right, with the distance between them, is to use an error function. An error function is basically the expectation of a loss function again. So suppose this is f, if this is our f, and if this is our h, okay, how do we measure the distance between them? Well, so here we have x, right? Okay, so here, let's say at this point, suppose this is x equal to -5, then the distance between them, right, this is the difference between them. Now, at x equal to 0, there's no difference. At x equal to 5, distance. At x equal to 10, this is the distance. So what is the overall distance, or what is the overall difference between h and f? To calculate that, what we do is, first of all, we define a loss function. Okay. So what is our loss function? Well, like we said, the loss function can be L1, L2, or the 0, 1 loss function, or many other loss functions. We can define loss function many different ways. If we use an L2 loss function, then the loss function is equal to fx. So at x equal to -5, that's x minus 5, f minus 5, right? Fx minus hx, which is this distance squared, right? So that's the loss function. So the loss function is typically defined pointwise. By being pointwise, I mean it's defined on each point, on each x. You can calculate the loss. What is the error? The error is really the total distance between these two, right? The total difference. The error is basically expectation of the loss function. Okay? So it's expected. Let me write this as Lx. Okay? So Lx equal to this. So this is L2, right? Then our error function would just be expectation of this. Now the expectation is taken over all the x. Okay? This is basically this distance squared times the probability of x equal to -5 plus this distance squared plus times the probability of x equal to 0, etc. Right? You add them together. And so this is with respect to x. Now, this error function is also what we call the E out. The out of sample error of this h. Okay? Now the reason why it's out of sample error because it's the underline, right? So this is assuming that we know the true f, we know that we have a h, and we calculate the expectation, which gives us E out. But in reality, we cannot calculate this E out, because in reality, we only observe a few data points out of this f. So suppose we only observe this point, this, right? If we only observe these 4 points rather than the entire f, then the only thing we can calculate is called in-sample error. Right? We're always only going to calculate in-sample error. In-sample error is equal to what? Well, it is equal to, very easy, the summation. So we have 1, 2, 3, 4 points. So it's 1 to 4, right? Summation of 4 points. And each point we have the loss function. Okay? So fxi, I will just write Lxi. Okay, right? That's the in-sample error. So I hope that's easy to follow. The loss function is defined for each point. For each point, we measure the difference between them using L2. If you use L1, then there's no square, right? Instead, we have absolute value. That's L1. The error function, which is a measure of the distance between the entire functions, is basically expectation of the loss function. But expectation can only be calculated, the true expectation can only be calculated on the underlying population, so that's E out. In the observed sample, we basically, right? People catch that, right? So there's 1 over 4, right? 1 over n, because we're doing the average of the loss function, expectation. Okay? All right, very good. Now, this is assuming that y equal to fx. So there's underlying f that we need to learn. What if y is not equal to fx? What if y is not completely determined by x? Instead, even after I tell you what x is, you will never be able to tell me what y exactly is, because y is not completely determined. In reality, that's the majority of the situation. So suppose we have this kind of situation where this is x, this is y, and the data, the underlying, the population looks like this. Right? So this is like the underlying population. It's not the observed data. So in the underlying population, even if you tell me x equal to 1, there are many possible values y. So you never know what exactly y is, because x do not determine y uniquely. Right? So y is not a unique function of x. In that case, we no longer learn something like fx, because y is no longer a deterministic function of x. So what we need to do in this case is to learn the distribution of y given x. Okay? Well, in this case, suppose x equal to 1, then y is no longer a fixed, so in this situation, if x equal to 1, then y is equal to f1, which is a fixed number, which is like something like y equal to 5. If x equal to 2, then y equal to 10, right? So every x value corresponds to a unique value of y. Here, when I tell you x equal to 1, y is not a unique point. Y is a distribution. There are many different possible values of y. Right? And we can always describe many different possible values with a distribution. Let's talk about that. So what we need to do is to find out the probability of y. That's the underlying, right? It's not fx anymore. It's the probability of y conditional on certain value of x. So for example, x equal to 1. When x equal to 1, y is still a distribution, and in the underlying population. And we want to know is we want to find out what this distribution looks like. And the question is, how do we do that, right? Now, well, very easy. I can, in this case, let's come back to this case. In this case, if y is equal to a deterministic function fx, how do I find out, or how do I learn this f? Well, I give a proposal, right? I make a guess. I say this f looks like this h. And then maybe I give it a model. A model is basically a set of different h, right? And I try to find the h that comes as close to this f as possible. That's how we learn f. Right? Make a hypothesis, try to find out the best hypothesis. It's a similar story here. In order to find out what the underlying p looks like, I'm going to give you different proposals. The proposal is maybe it looks like this, maybe it looks like that, and we're going to try to find out the hypothesis that's closest to this true underlying p. For example, I can say maybe, because I do not know this p, all right? So maybe I say maybe it looks like this, okay? The uniform distribution, right? So maybe y is uniformly distributed given x. Or I can say maybe it's the normal distribution. So that given x, y is a normal distribution. Or maybe it's some other kind of distribution. So in other words, I can guess, I can make a hypothesis of what the distribution of y looks like given x. So I use q. Q is also probability. So p, I use p to denote the underlying true distribution. I use q to denote my hypothesis. Just like h and f in our story before, right? And my goal here is to find out, so I can give you a hypothesis set, right? So I will give you, so I still use the large H, right? The large H is our set, our model. It's a model, it's a set of many different hypotheses. Now, our model contains many, many, many Qs, okay, distributions. Okay? So Q, Y given X, but this is my first hypothesis. This is my second hypothesis, and I have many, many hypotheses. Right? Remember, in this case, our H is H1X all the way to HMX and some more, right? So our hypothesis contains many individual H. Here, our hypothesis that the model contains many different Qs, which are my hypothesis. And what I'm going to do is I'm going to pick one Q from this set that that come closest to the underlying P. just like what we did before when we picked the optimal H that's closest to the underlying F. So it's the same story. We're just replacing function with probability distributions. However, what is new here is that we somehow now we somehow need to measure the distance between distributions. Remember here what we need to have is we need to measure the distance between two functions, right? H is a function, F is a function. This is how we measure them. We define the loss function, and we calculate the average of them, right? The expectation or the average, which is our error. The error is a measure of the distance. Here we have distributions. This white thing, this white line is the true distribution. This yellow line is my hypothesis. So what is the distance between this yellow and this white? How do we measure the distance between them? In other words, how do we measure the difference between two probability distributions? That's something new, right? Okay. So I'm going to spend some time to introduce essentially a common measure of distance or difference between two probability distributions. Here, the loss function is the L2 loss function is used to measure difference between functions. When it comes to probability distributions, we are going to use something called KL divergence. So, now let's forget about y and x for a minute. Let's just say I only have x. Okay, there's no y, there's just x. So the underlying true distribution of x is px. That's our true distribution. And now I have a proposal. I have a hypothesis. The hypothesis is I think the distribution look like this. Okay, that's my hypothesis, and my hypothesis is qx. Okay. Right. So this is x. This is the this is the distribution frequency of the PDF of the x. Right. So this is my hypothesis. This is the true distribution. How do we measure the difference between them? We use something called KL divergence. And the KL divergence is defined as this dKL. Now that's just, okay. I would say P given Q. This is a fancy way of writing KL divergence. It basically means the difference of Q from the true P. P is the true one. Q is my hypothesis. And it's defined as, well, I will write in discrete. Okay, so this is continuous, but for simplicity, let's write discrete case. Discrete case is basically summing over different values of x, and at each of the different value of x, I have log px over qx. Okay, square px. Okay, so that's our definition of KL divergence. It's a measure of the difference between two distributions, P and Q. Now you have never seen this before, so let me explain, right? So why can we measure the distance? Why can we measure the difference between two distributions using something like this? Well, first of all, what if these two distributions are exactly the same? What if my Q is the true P? What happens to this KL divergence? It's equal to 0. Very good. Okay. When they're the same, it's 0. So very good, right? Because if we want to measure the difference, I want this measure to be 0 when they're the same. What if Q is different? If Q is different from P, can you tell me whether this is larger than 0 or smaller than 0? Can you see that? It's larger. Why? Yes, very good. Okay, according to Jensen inequality, you can prove that this is larger than 0. Right? Now, intuitively, it's also pretty obvious. You can just look at this because why? Look, when P is large and Q is small. So let's look at here, right? In this point, when P is larger and Q is small, what happens? This is larger than 0, right? Okay. Now here, Q is large, P is small. This is smaller than 0. However, even when this is smaller than 0, this P is also small, right? Okay. When Q is large, P is small, this P is small. So even if this is smaller than 0, it is timed by a it is multiplied by a very small number, right? Weight, very small weight. But when this is positive, it is typically multiplied by a larger weight. So in the end, it's always going to be larger than 0, right? You can think about that way. So it's always going to be larger or equal to 0. That's why it's distance measure. It could be used as a measure of distance between two different distributions, right? Now, the more dissimilar P and Q is, the larger the KL divergence is. So we're going to use KL divergence as a measure of distance between two distributions. All right. Now, where does this KL divergence ever come from? Right? Where does it come from? It comes from information theory. So I'm not going to spend a lot of time going into detail again because it's not central to our course. But you can read it in appendix. Okay, some basic information theory. Now, let me just briefly talk about what does KL divergence mean in terms of information theory. All right. So let's take a look at this thing. Okay. So I'm going to define something called HP, and which is equal to, again, let's do the discrete case, summing over different values of x, px log 1 over px. I'm going to define something like that, and that has a name in information theory, which I'm not sure you have heard about, but it's called entropy or Xiamen entropy. This comes from physics. Okay, the name entropy comes from thermodynamics, from physics. But in information theory, we define entropy as this definition. And you can prove, right? We can prove, which I'm not going to do today, but we can prove that if this log is log 2, if the base is 2, then we can prove that this number, okay, is the lower bound, is the minimum amount of bits, 0, 1 bits, needed to encode a distribution of random variable x. Let me explain what that means. Okay, so suppose I have a random variable x. This x has 8 different values. There are 8 different states. Okay, 1 to 8, 8 different values. What we can do is, remember, when we're using computers, it's always, we want to encode them into bits, 0 and 1 bits, right? If x has 8 values, how do I encode x into 0, 1? Well, one way to do it is I can say when x equal to 1, I encode it as 0, 0, 0, right? And I have 0, 0, 1 for the second value. The third value would be 0, 1, 0, and 0, 1, 1, all the way to 1, 1, 0. So there are 8 different possibilities, and I can encode them using 0, 1. But how many bits do I need? 3, right? So I need, on average, 3. The length of the bits I need to encode them. Sorry, 1, 1, 1. So on average, the length of the code I need to encode is 3. Okay? 3 is the average length. All right. Now, what is 3? How do we get this 3? Okay. When x has 8 states, I can encode x using on average, length equal to 3, right? 3 different 0, 1 bits to encode this x random variable. Now let's take a look at this entropy, right? Suppose 1 to 8, the probability of each state is all 1 over 8. Suppose every state has 1 over 8 probability. What is the entropy? What is the log? So px is equal to 1 over 8 for each state, right? So what is log 2 of this? 3, right? Correct? So we basically have 3 times the probability of 1 over 8, because each state is 1 over 8, but then we add them together. So what is the final number? 3. And that's the number of bits we need to encode the random variable. Okay. So in other words, this is an example to show you that entropy, which is this thing, is a lower bound. It's the minimum amount of, on average, the number of average bits we need to encode a random variable. Now, in order to this is only a lower bound. By lower bound, I mean the least number of bits, okay? The least number of bits, the length of code we need to encode. And so it's not really easy to achieve this. To achieve the lower bound, because typically if you use a coding system, if we use an encoding system that is different from this one, typically we need more length to encode that. So in order to achieve this lower bound, we need optimal coding. That's information theory. If you don't understand, this is perfectly okay, right? So the idea is what is the optimal coding? Well, here we're actually using the optimal coding. But what if I do not use optimal coding? Then I need more number, right? So now I'm going to define another thing, another concept, which is here, right? I'm going to define something called HPQ, right? Just two things. I'm going to define it as the sum of xpx, okay? And again, log, using 2 as a base, 1 over qx. This is called cross-entropy. So this is called entropy, right? Just entropy. Or Xiamen entropy. This is called cross-entropy. The idea of cross-entropy is, suppose this px is the true distribution of x, but I do not know it. I use qx to encode. So I use a coding scheme that is best for qx, which is a different distribution, to encode x. But in fact, x is actually p, not q. In this case, what is the average number of bits I need to encode this x? That's called cross-entropy. So in other words, cross-entropy is using a wrong, or at least a not optimal coding scheme. If you think it's another distribution, but in fact in fact the distribution is not what you assume, then that's cross-entropy. This entropy is the optimal coding scheme, which is you know the true p, and you use the optimal coding, then you get the least number of bits. Now, if you use the wrong, or at least not very good, if your guess is different, if you use q instead of p, then you use more bits. So cross-entropy is typically larger than entropy, right? Okay, you can think about that. We use more bits to encode a random variable. So as an example, let's take a look, right? Again, let's use this example here. Suppose again that x has 1 to 8 different possible states. Now, remember, previously what we do is we encode using 3 bits, right? So we have 0, 0, 0, all the way to 1, 1, 1. We use 3 bits to encode this x random variable when the probability is 1/8. The probability is 1/8 for each, all right? Now, however, suppose now that the true distribution is not this one. This is not a true distribution. The true distribution is 1/2, okay, this is 1/2 probability. The second is 1/4. The third is 1/8, right? And then we have 1/16, 1/64, and all the 1/64, the rest of 1/64. Okay? So the 8 states have different probability. So this is the true probability p. P is not different from uniform. But, okay, we believe this is q. So we believe it's uniform distributed. But in fact, it's not uniform distributed. Well, as long as we believe it's uniform distributed, this is our best coding scheme. We are using 3 bits. But what is the actual best coding scheme? If we know the true p, then there's a different way to code it, okay? Our coding is basically, we'll use 0 for the first state, 1, 0 for the second state, 1, 1, 0 for the third state, and we can continue until 1, 1, 1, 1, 1. Okay, 6 bits in the end for the last state, for the 8th state. In other words, we're going to use a short code for events that are highly probable. We're going to use long code for events that are very, very unlikely to happen. In that case, the average amount of coding we need to do for this random variable can decrease from 3 to 2. Okay? You can do the math yourself, right? I'm going to, which is basic here, because with with 0.5 probability, I only need one. So if we do this, right? Remember, the first state has probability 1/2. So with 1/2 probability, I only need 1 bit to code the random variable, correct? And then with 1/4 probability, I need 2 bits. With 1/8 probability, I need 3 bits. So in other words, the highest probability event, I make it the shortest. So then when you add them together, the average number of bits, the expected number of bits, is smaller than 3. Now here we have 6 bits, which is very long, but I don't care because this has very small probability of happening. So I probably never be, not never, but I have a very small probability of having to use 6 bits to encode it. Most often, I only use 1 bit or 2 bit. And that's how I decrease the average number of bits from 3 to 2, right? So I only need 2 bits rather than 3 bits. So in other words, here the entropy is 2. If you calculate using the entropy, you get 2. And that's exactly the optimal coding, right? The entropy is 2, which is if you use the optimal coding when you believe the true probability distribution, when you know the true probability distribution. However, if you do not know the true probability, if you use a coding scheme for the different distribution, like uniform, but actually it's p, then you have to use longer coding. So now it's equal to 3, but this is equal to 2. So cross-entropy is the essentially longer, right? Because you're using incorrect coding if you think about it that way. So what is KL divergence? Do you see from this distribution, from these two definitions, do you see their relation to KL divergence? So let me remind everybody what KL looks like, right? What does KL look like? Okay, so this is what KL looks like. So what is the relation between KL and cross-entropy and entropy? KL is what? Let's forget about base 2, right? Forget about it, just log. So what is KL? Yeah, very good. Which one minus which one? Yes, cross-entropy minus entropy, right? Okay, so KL is basically cross-entropy minus entropy. Okay, so what is our interpretation of entropy? Entropy is the optimal coding. Cross-entropy is the coding you use when you wrongly believe the distribution is Q, right? Q is P, but you use Q. So this one minus this one is what? Is the additional bits you use to encode a random variable when you believe that the true distribution is Q rather than P. So in other words, when you use a distribution that is not true, what is the additional, what is the unnecessary amount of bits you are using to encode this variable? That's KL divergence. So the larger the KL divergence, it means that the more wrong, right? The more wrong your assumption of Q is, okay? Your assumption of the distribution is. That's the definition of KL divergence from information theory. Now, when you use KL divergence, so we use concepts of cross-entropy in data analysis, in our analyzing data, we don't really need to understand its information origin. In information theory, all we need to understand is that KL divergence measures how far away your assumption of Q is from the true P. And cross-entropy is essentially just KL divergence plus the original optimal coding, right? The entropy. Okay, so that's the idea. Now, I don't really want to spend time, but I still want to spend maybe a few minutes on this very cute example, because the example is fun. Right? I think we all understand the concept now. Let's just go over just one more example. So this example is I have a bag of 4 coins of different color, blue, red, green, and orange. Now I'm going to draw a random coin out of them. So I'm going to do a uniform distribution, right? Randomly draw with equal probability. So I want you to guess which color of the coin is. How many guess? My goal is, my question to you is, what is your best strategy to guess the color of coin? And by best strategy, what I mean is, can you design a strategy so that you ask the least amount of questions? The less number of questions you ask, the better. The fewer number of questions you ask, the better. What do you do? Well, a very easy one to think about is you can just use this very simple strategy. So you pick a color, right? You say, is it blue or red? We have 4 colors. You first ask, is it blue or red? If I tell you yes, then you say, okay, is it really blue, right? So the second question is blue. With two questions, I can differentiate between blue and red. Now if I tell you no, then your second question is it green? Then you can get, right? So that's a very simple way to ask questions in order to determine which color it is, okay? So on average, how many questions are you asking? On average. What is the expected number of questions you're asking? 2, right? Because to reach any conclusion, you need 2 questions. And they are all the same probability, right? You know, it doesn't matter even if they're... So 2 questions is what you needed to get the correct answer. Okay? Now, and that's basically the entropy, right? This is basically the entropy. Remember, the entropy is how many bits we need to encode a random variable given distribution. This is basically the entropy, the number of questions you need to ask in order to figure out, right, what the color it is for the uniform distribution. Now, suppose I tell you that the color has different probability. So 1/2 of the coins is blue, 1/4 are red, 1/8 are green, and 1/8 are orange. Suppose that's the case. Do you still use this strategy to get the answer to the color? Well, you can still use it, but it's not going to be optimal because the true distribution is no longer uniform, right? So we can change to a different strategy. So this will be look at this, right? This is basically a different strategy, which is I first ask you whether it's blue or not. If it's blue, I directly get my blue, right? If it's not, then I ask is it red, then I'll ask is it green. Why in this case, what is the average amount of question you need to ask? Well, with 50% probability, because blue takes 1/2 of the coins. So with 50% probability, 1 question is enough, right? So 50% times 1 plus 25%, 1/4 probability, I need 2 questions. And finally, 1/8 probability, I need 3 questions. So if you add them together, I only need 1.75 questions, okay? Which is less than 2. We have lowered the amount of questions we need to ask. The trick here is that you always want to use a strategy such that you shorten the amount of questions you need to ask for high probability events. So for the highest probability, you try to get it directly. For lower probability, you can ask more questions, just like the example I gave before, right? And so that the optimal one is 1.75. So in this case, for this probability distribution, the entropy is 1.75. Now, can I still use this strategy? Can I still use this strategy to guess the color of coin, even if the probability distribution is like this? Of course. It's just that it's not optimal anymore, right? You take more answers, there are more questions. So if I still use the original strategy for this new distribution, what is that called? This is called entropy, right? 1.75 is the entropy for this distribution. If I still use my old strategy and I get 2, I need 2 questions on average to get the correct answer. What is that called? That's the cross-entropy. So the cross-entropy is using the wrong strategy, or basically assuming the wrong distribution, right? So suppose this is the true distribution, but I do not know it. I still think it's uniform. I still believe my Q is uniform. Then I still use the original strategy that it takes me 2 questions to say it. So that's essentially cross-entropy. So cross-entropy is 2, and the entropy is 1.575. What is KL divergence? 0.25, right? KL divergence is basically the difference between the two. Okay? How many additional questions we need in order to answer if we assume the wrong distribution, right? So that's the from information theory example, sort of an origin of all these different concepts. Okay, so let's go back. Sorry. Okay. So let's come back to analyzing, so data analysis, right? Analyzing data and doing statistics. Now, like I said, our original goal, remember what our goal is. Our goal is I give you a px that's the true distribution, but I do not know it, so I have a proposal. My proposal is this q, it's my qx, and now what I'm going to do is I'm going to use KL divergence to calculate the similarity, right? I'll calculate the distance. So my KL divergence again is defined. Now this is continuous, so now I'm going to write it in continuous form. We're replacing the sum with the integral, right? So log p x qx px, okay? Dx, right? I can write it this way. So this is going to be my KL divergence that measures the difference between these two distributions, with p being the true distribution, q being my hypothesis, which is typically incorrect or not the true distribution, right? Okay. Now the problem is, so I'm going to say this is going to be my error function. This is my error function. Right. Remember, error function is basically a measure of dissimilarity, right? How different they are. So this is going to be my error function for distributions. Right? Again, my error function for functions is something like this. My error function for distribution is KL divergence. Now, what is the loss function here? What is the loss function? If this is the error function, what is the loss function? Can you tell? Let's come back to this case, right? Between h and f, the error function is the expectation of the loss function, right? Okay. So, if this is the error function, what is the loss function? So the KL divergence, so KL loss function is basically, if people can see that, it's basically log px. That's the loss function, right? Because this one is the expectation of this one. True? This one is the expectation of this one because the true distribution is p, right? So when you integrate it with respect to p, that's the expectation, okay? Right. So people get it? This is basically, the error function is basically the expectation of log p over q. Huh? Now again, I cannot calculate it because I do not know the true p. In reality, I only know what? I only see a few data points that are drawn from distribution, right? So I don't see the true p. So just like the case here. Here, we do not see the true f. So this error function is called out-of-sample error because it's something that we do not observe directly. Now we can calculate in-sample error, which is the error function based on the observed data points. Here, it's very similar. Our KL divergence is basically our out-of-sample error. What is our in-sample error? It's also very simple. It's basically so out-of-sample error is the expectation, which is the underlying true, right, distribution. In-sample, we just replace it with the average. Okay? So 1 over n, summation, I from 1 to n, these are our observed data points. Sorry, I should, right? To make it clear, right? Then we have log, okay, p xi divided by q xi, correct? Now, some people are going to ask, well, I cannot calculate this either because I never know pxi, right? So I will address this issue very soon. But you can see, you can understand, the first step is let's understand out-of-sample error versus in-sample error. Out-of-sample error is the expectation in the underlying distribution. In-sample error is the average on our observed data points. Okay? That's KL divergence in-sample error. All right. Now, what is we can also talk about. Well, let me just continue from here. All right. So, remember what we are doing here, right? Here, when we have h and f, we have functions, what we do is, yes, this is the outer sample error, but we can only calculate the in-sample error. And when we are trying to find out the best hypothesis, what do? Well, we pick, oftentimes, right, typically, we pick the hypothesis that give us the smallest in-sample error, correct? Right, so that helps us to drive E to 0. And then I need my model to be not too complicated so that the VC dimension not too large. So after E is very low, I can say E out is also very low, right? So that's the process, 2-step. But the first step is when I'm fitting my model, when I'm estimating my model, I'm choosing a hypothesis that gives me the smallest E. That's typically the case, right? Okay? Everybody sure on that? So we'll make sure that everybody knows. So when we're doing data analysis, when we're estimating our functions, estimating our model, our model has many different h, right? And how do I pick any one of them? Well, I pick the h that give me the smallest in-sample error, typically, in many different algorithms, okay? So that's the way it is typically done. Here, what I can do the same thing. I give you a model, and this model is consisting of many different distributions. Okay? From Q1 to, let's say, Qm, I give you n different hypotheses. Each one is a different distribution. I want you to give me a Q that is closest to the underlying P. What we can do is I can find out a Q that minimizes the in-sample error, correct? Because we never see the outer sample error. We can minimize the in-sample error. Now, so that's why we need a measure of distance. So once we have a measure of distance, like a KL divergence, then we can do optimization. We can choose a hypothesis that gives me the smallest in-sample error. Now, if I want to minimize the in-sample error, how do I do it? I basically pick the Q that gives me the smallest number, right? So, right, okay. So let's see. So I want to minimize this in-sample error. And this in-sample error is equal to minimize the summation of log, okay, P over Q. So I can write it as PXI minus, PXI minus log QXI, right? I can write it this way. Can I? I from 1 to n, 1 over n. So I want to basically find out a Q pick a Q from my hypothesis set H, so that this thing is minimized. And when I do that, first of all, I can get rid of the 1 over n, right? Whatever minimize the sum. Second is I can get rid of the P, right? Because P is the underlying true distribution. It never changes. And I'm just picking a Q that minimizes this thing. So P doesn't matter to me, right? Remember, we're choosing the best Q. So I can basically delete the P. So look, we're left only this one. Let me write it. We're basically minimizing negative log QXI. Now, can I do that? Of course, right? Of course I can minimize this. Can I calculate the in-sample KL divergence? Actually, no, because I do not see the P. So I cannot calculate the in-sample KL divergence. But I can minimize it, because the P doesn't matter to me when I minimize. So in the end, I just minimize this thing. And that will give me the best Q. That's how we find out the best hypothesis distribution to describe the underlying distribution. Just like that's how we find out the best H to fit the F. Here we minimize this. But what is this thing? What is this thing actually? How do we actually describe, this object? Well, it turns out that let me do a little bit more derivation for you. All right. Remember what cross-validation is? Oh, sorry, cross-entropy. Remember what cross-entropy is? Cross-entropy is defined. Now I'm going to write in integral again. Replace the sum with integral. Integral, remember, cross-entropy is the log of, it's basically the log of 1 over qx and then times px dx, right? Do people remember? Let me go back, all right? So where's the cross-entropy? Okay. Right, so if we look at here, this is our cross-entropy. And previously I write it in discrete form, but nowadays I'm here just writing in integral. It's using still px, but I'm using the wrong distribution, q, right? So it's basically log of 1 qx, px dx if we do it integral. Now, if I want to write, we can also write it as expectation of the log of 1 over q, right? It's basically this version of this. What is the in-sample version of cross-entropy? Suppose I do not observe the entire distribution. I only observe a few data points. What is the in-sample version of cross-entropy? It's basically 1 over n again, summation of y1 to n log 1 over qx I, correct? I'm just replacing the expectation with the average, in-sample average. That's the in-sample version. Now, what does this look like to you? They're the same, right? Okay. Right? So what is this? This is simply the in-sample cross-entropy. That's what it is. Okay, so I know this can be a little confusing to all of you, but let me just summarize, all right? We're getting there very quickly. I use Kl divergence to measure difference between my. So this is my summary, right? Kl divergence measures the difference between my proposal Q is my hypothesis, from the true distribution P. Now, when we do estimation, we pick the best Q from H, right? We pick a Q from H that minimizes to minimize in-sample, okay? In-sample KL divergence, right? Because we only see in-sample data. Now, in data science, we often call in-sample, we also call it empirical, right? So you often hear people say empirical KL or empirical cross-entropy. It's the same thing, in-sample KL divergence. But it turns out that minimize in-sample KL is equivalent to minimize in-sample what? What do we get here? In-sample what? Cross-entropy, okay? Cross-entropy. Right? So minimizing in-sample KL is equivalent to minimizing in-sample entropy. That's basically the story I have told so far, all right? Now, if we minimize in-sample cross-entropy, what is the loss function? What is the loss function here? Remember, this is our error, right? The error is the expected loss function, or average loss function. So the loss function here is very simple. The loss function is simply negative log qx. That's the loss function. And this loss function is also called cross-entropy loss. So we have a special name for it. I'm going to name it cross-entropy loss. So in other words, when we are trying to pick the best distribution, hypothesis distribution to fit, when we're trying to pick the best hypothesis to fit a distribution, the loss function we use is cross-entropy loss. And the reason why we use cross-entropy loss like this is, again, because this, I will not repeat, but we use cross-entropy loss when we are fitting distributions. That's basically the story. When we are fitting functions, not distributions, like the H and F, then we use loss function like L2 and L1. So L2 and L1 loss functions are used for functions like H and F. Cross-entropy loss is a loss function we use when we are fitting distributions. So that's really the final conclusion of a long-winded discussion that took us to information theory and everything else, right? But if you get that, then you get the main point of the distribution of the discussion that we have so far. All right. Has anybody seen cross-entropy loss and Kl divergence before? Is this new to everybody? But you have all studied econometrics, right? So in econometric statistics, how do you fit distributions? Because look, when I say here, right, I say when we're fitting distributions, we use cross-entropy loss. We minimize this. But this is all new to you, which they should not be, because you have fitted distributions before in your class, right? So in your econometrics class, also in your statistics class, how do you fit distributions? Do people remember how do you do that? Sorry, who said that? Somebody said MLE. Who? You? Okay. All right. So how does tell us how does MLE work? Okay. So in your course, right? In the course you have taken, econometric statistics, whatever, you have all learned maximum likelihood, correct? Maximum likelihood estimation, which is also called MLE. Okay. Now, how does MLE work? Maximize what? Yeah. So let me just say, okay. Suppose you observe some data that suppose you observe some y, okay, and I'm trying to describe the distribution of y. All right. Now I have some hypothesis. I think maybe y is this normal distribution with mean mu with variance sigma squared. Right? Okay. Now suppose I know the variance. I know for sure the variance is y. I just don't know the mu. How do I find out the mu? Using maximum likelihood. This is the simplest maximum likelihood we can ever think about, right? How do I find out? Well, you observe a bunch of data points, right? So you say you observe y1 to yn. These are the data points you observe. And you say, okay, all right. If y1 equal to, let's say, 2, then I will calculate what is the probability of y equal to 2 if y is this normal distribution. Correct? According to this normal distribution. So if y is this normal distribution with this mu, what is the probability of y2? And then I can calculate what is the probability of yn equal to, I don't know, maybe it's equal to -1, so -1. According to my hypothesis, what is the probability of each of the points? And then what do I do? Is it really some of them? You multiply them, right? No? I'll tell you why. You say sum, which is correct in a sense, but let me show you, all right? So what you do is you calculate something called a likelihood function. The likelihood function is the probability multiplied together, okay? y1 equal to 2 times, sorry, according to this hypothesis, y1 equal to 2 times times probability of yn equal to 1. You time them together, and you find the optimal mu that maximizes this probability. However, when you do that, it's equivalent to finding the mu that maximizes the log of this thing, right? I can take a log, maximize the same thing, but once you take a log, it becomes a sum, right? So that's what I did, okay? So if you see the sum of log probability of y given my hypothesis mu, right? Given that, I assume that it's a normal distribution with mu. So I'm basically find out my mu that maximizes this, correct? So this is the story of maximum likelihood. Sorry, let's go back. Okay. So in other words, what we do. In other words, what we do in maximum likelihood is I do not know the true underlying distribution. So I have a proposal. The proposal is Q. And in fact, I have a model. The model each has many, many different Q. Okay? Q1 to Qn, many different Q. I'm going to pick a Q. How do I pick a Q? Well, I calculate the sum, okay, of the log, right? The sum of the log of my hypothesis Q. Correct? Qxi, that's what I did, right? Qxi, log, sum together I from 1 to n, and then I basically choose the Q that maximize this thing, correct? That's maximum likelihood, right? Everybody agrees? My example? But what is this? The same thing, right? So maximum likelihood is the same as minimizing Kl divergence or minimizing cross-entropy. Okay? So minimizing Kl divergence is equivalent to minimizing cross-entropy in sample, but then it's also equivalent to maximizing maximum likelihood. So in other words, you can think about maximum likelihood as minimizing the distance between two distributions. And the distance is measured by Kl divergence. So in other words, maximum likelihood is within this big picture of first defining our loss function and defining distance and then minimizing it, okay? So defining a distance and then minimizing it is the whole unifying theme of how we do data analysis. Maximum likelihood, despite its name, is also part of the family. It's the same story. It's just that the distance here is defined by Kl divergence. And the loss function we use, you can think about maximum likelihood as minimizing the cross-entropy loss. Okay? This is the cross-entropy loss. And maximum likelihood is minimizing cross-entropy loss. So again, we have I'm not really teaching you, in other words, I'm teaching you nothing new at all, okay? So this is something that you have already learned. I'm just putting it in a different framework for you to understand, right? In a picture. Okay. All right. So minimizing the empirical Kl divergence or minimizing cross-entropy is equivalent to maximizing the log likelihood function. It's the same thing. All right, okay. So that's it. Now, let's go to our next step. So, remember the big picture we have, okay? We have a bunch of x, we have a bunch of y, and given any x, suppose x is equal to 4, there are many, many different possible y values, because y is not determined by x. So basically, at x equal to 4, I have a distribution of y. And the distribution is py given x equal to 4. I do not know what this distribution looks like, so I give a hypothesis q from a large set, from a large model. I'm going to pick my q to describe the p. That's the story. So now suppose this is done. Suppose I've already picked my best q, okay? Q1x. So this is my best. This is the one that I pick from the set by minimizing cross-entropy loss or by maximum likelihood. Right? Suppose I've already done that. I've chosen my best q. Let me use a different notation. Let me write it as p hat y given x. Okay? because the true distribution is P. And I'm going to just use P hat to say that's my estimation, okay? That's my best fit. Now now the question is, suppose I already know P hat given Yx. I already have that. What do I do? How do I predict Y? Because oftentimes people still ask you to make a prediction. So give me just one value of Y. I don't want a distribution. I just want you to predict the value of Y if I tell you X. What do? Now you have already estimated. So this is a P hat. P hat Y given X. Okay. This is X. Well, this. Yeah. Okay. So I've already suppose I tell you, please help me predict the value of Y if I tell you X equal to 4. Can you give me a Y hat? Can you help me predict Y? Well, you say, okay, because Y is not completely determined by X, I first need to estimate this thing, P hat Y given X, equal to 4. Now that I have estimated this thing, I can use it to make a single prediction Y. But what Y should it be? Do people know? So suppose this is your estimation of this probability distribution, and I want you to make a single prediction. Just one value. Give me one value of Y. What value should I give? I think we have already talked about this question at the very beginning of this course, remember? Where I give you a distribution of Chinese income, and I say, if I just want you to give me one guess, right, just one prediction of the income of any random person from the distribution, what number should you give me? The answer is you can give me many different numbers depending on the loss function again, right? Here it's the same. I'm sorry, this is ridiculous. I speechless, all right? So somebody should talk to, maybe I should talk to them. What's my question again? Well, terribly distracted. All right. So, loss function, yes. So what loss function should we use? Well, again, it depends on your choice. If you choose L2, then we predict the mean, right? Then our prediction is the mean of Y given X according to this P, right? Now, if you use L1, then what do you get? The median, right? The median. Also, if you use let's suppose you use a different kind of loss function. If I use a loss function of I, Y equal to Y hat, not equal to, so if it's not equal to, it's 1, if it's equal to 0, what number should I predict? No, not median. Median is L1. Mean is L2. If I use this has a this loss function is called 0, 1 loss, by the way, because it has only two values. Okay, 0, 1. So we use 0, 1 loss. My optimal prediction is this so-called. I have a better graph here. I don't have to draw it. Okay. What am I doing? So suppose this is the P hat. Then the mean is this red line. The yellow is this. Yellow is the median, and this is called a mode. Mode is the point where it's the highest probability point. So if I use L2, it's the red one, mean. If I use L1, it's the median. But if I use the 0, 1 loss function, I get the mode, okay? I get the highest point here. Now, in other words, let's come back to our origin, very initial, our mission at the very beginning. Our mission is I give you an X, you please predict Y hat, okay? Let's produce a Y hat. I give you an X, please predict Y for me. So, I've talked about two situations. The first situation is Y is a deterministic function of X. Y is completely determined by X. In that case, it's very easy. I find the optimal H that's closest to F, and then I say Y hat is simply HX, correct? It's very easy, okay? Or I can say F hat. Doesn't matter, right? I pick something that's very close, and then Y is this. But this is only the first situation. The second situation is Y is not completely determined by X, which is by far the majority of the cases. In this case, even if you give it, there's no such deterministic function there. So in this case, we can do two steps, okay? In order to produce a y hat, I have two steps. The first step is I find out the optimal p hat given x. So I estimate the conditional distribution y given x. Right? That's the first step. The second step is I produce y hat based on this p hat. How do I, right? And the second step is what I describe here, right? Okay. So this is my estimated p hat. And given p hat, I can produce a y hat. That's the second step. And the interesting thing here is these two steps use different loss functions. In the first step, we minimize cross-entropy, or KL, okay? We minimize KL. In the second step, we minimize any loss function that you pick, like this, right? Like L2, L1, 0, 1 loss function you can pick, right? Because they are actually separate steps. This step is mainly estimating the distribution. This step is making the optimal prediction given an estimated distribution. So you can choose different loss criteria in these two steps. All right? Okay. What if y is discrete? So the case, the example here, this y is continuous. What if y is discrete? What should I? How should I make a prediction y? Now, suppose y has only 3 values, okay? So y is equal to 1, 2, 3. There are only 3 values of y. Let's suppose that I already have a p hat. And the p hat is, if y equal to 1, I have, say, 30% probability. If y equal to 2, y equal to 3, y equal to 3 is also 30% probability. Or maybe let's make it 35, okay? So just a little bit higher. Well, no. Let's say 25%. A little bit lower. And then y equal to 2 is 45%. Okay? All right. So that's my estimated p. Okay? That's my estimation. Now, if I want to make a single prediction of y, which value of y should I predict? Should I predict y equal to 1 or 2 or 3? 2. Why? Because it's the most high probability. Well, the answer is you can predict any one of them. Again, why? Because it depends on what? The loss function. What kind of loss function give you y equal to 2? Remember, y equal to 2 is the y value that is the highest probability. What loss function is that? Remember? What loss function give you the highest probability? 0, 1. So in this case, if you use 0, 1 loss, you should predict y equal to 2. But if you use different loss function, actually you get different answers. So let me show you, right? Now, the 0, 1 loss function, we can write it this way, okay? So suppose y value goes from 1 to k. Y value, right? So this is the true value of y. This is your predicted y value, right? Now, the 0, 1 loss function basically says if your prediction is exactly the same as the true value, my loss is 0. But as long as they're different, it's 1. So everywhere is 1 except the diagonal is 0. Okay? If you minimize this loss function, you basically, now if we minimize the expected value of this 0, 1 loss, it's the same thing as minimizing the probability of y does not equal, right? So let's, if I minimize expected y value of y not equal to y hat, it's equivalent to minimizing what? What is this expectation equal to? Do people know? What is the expected expectation of y equal to a? If you maximize, this expectation is equal to it's just equal to the probability of y equal to a. Everybody gets that, right? So minimizing this expectation is the same thing as minimizing the probability that y does not equal to y hat, right? Which is maximizing the probability that y equal to y hat, right? Okay, so I basically need to choose a y hat that has the highest probability, correct? So that gives us this one, right? Y equal to. So minimizing the 0-1 loss basically means you're picking the one with the highest probability according to our estimate, right? And in statistics, we call it the Bayes classifier, meaning the Bayes classifier is basically choosing the value that has the highest probability using the 0-1 loss. We'll talk about that later, okay? But is it always true? Is it always the best for us to use the 0-1 loss? Well, in other words, is it always the best for us to pick the one with the highest probability? No, the answer is no. Let's take a look at some example. But first, let's imagine another case where y has only two values, -1, +1. So the true value is +1, -1. Your prediction is +1, -1. Now, if your prediction is correct, we say there's no error, right? But if your prediction is incorrect, there are two cases. If the true value is -1, but you predict it to be +1, we say that's false positive. People familiar with that, right? If the true value is +1, but you predict -1, we say it's false negative. Because it's not negative, you're falsely negative, and here's no error. Okay? Now, false positive and false negative are both error, but they're both undesirable, so we don't want it, right? So we want to penalize the error. Right? So we want to give a penalty to the error, right? How much penalty do we give? Well, the 0-1 loss function gave how much penalty? 1 and a 1 here, right? The 0-1 loss function says 0, 0. If there's no error, that's 0. But as long as you are different, I'm going to penalize you. I'm going to give you a penalty of 1 so that you better not have it, okay? However, this may not always be the best choice. So let's imagine this situation where y is actually your fingerprint, whether the fingerprint matches with the data or not. So if you imagine we're doing a fingerprint scanning. So a person comes in and put a fingerprint on it, and you have to decide. The algorithm has to decide whether this person is the true person or the wrong person, right? Now, if you get it wrong, if the person is not the right person, and you say he is, that's false positive. If the other case, if the true person is the correct person, but you refuse him, that's false negative. So, let's take a look at two examples. Suppose the first example is supermarket, right? Now, in the supermarket, suppose maybe not fingerprint, but suppose a person is a loyalty loyalty customer. Is a loyal customer, and you want to give him a discount. So the way that this supermarket does is that maybe they collect fingerprints. Okay, just suppose. So you just fingerprint it, and it says, okay, it's you. You are my loyal customer. I give you a discount. In this case, what type of error are you worried about? Are you worried about giving discount to a person who is actually not a loyal customer? Or are you worried about not giving discount to a person who actually is your loyal customer? Which one are you more worried about from a business perspective? Are you worried about false positive or false negative? In other words, that should be an obvious answer. Unless people do not understand business, right? Sorry? No. You should really be worried about not giving discount to a person who actually is, because that makes people angry. Now, if you give a person discount, but that person is not loyal member, what is he? Well, you only lose a tiny little bit of money. You only lose a tiny little bit of money, but that person actually would be happy, right? And that person may come back to the supermarket more to buy your things, right? So you're not that worried about giving tiny little bit of money to people who are not. But if you piss somebody off, okay? If you make somebody angry, well, I already purchased your membership and you don't give me discount, I will be extremely angry at people. That's a psychology, consumer psychology. So you really worry about, again, false positive or false negative? Which one? False negative, okay? You're worried about false negative. So in order to minimize false negative, in other words, this is not important, this is more important to you. So we really want to minimize this. So in order to minimize this error, we should penalize it. We should give a higher penalty than 1. So what I can do is for the supermarket, I can say, I'm going to say 10 here. Not 1, but 10. I really want to penalize this. Okay? Now, on the other hand, imagine you are a high security National Security Bureau, okay? The Central Intelligence Unit of China, or the CIA or FBI, whatever, right? And in your building, you want to use fingerprint to control who gets access, who can enter the building, who cannot enter the building. In that case, are you worried about false positive or false negative? Of course, false positive, right? You don't want any bad guy to get in. But if you refuse once in a while, if you refuse some true employee, who cares? That person can just call and somebody help me, right? So you really care about false positive. So in that case, your loss function should be probably something like this. Okay, the false positive is 1,000. You really don't want this to happen, and you don't care about this that much. Now it turns out that if you have different loss function, your prediction, the y hat, will be very, very different. Okay, now. So here y has only 2 values, right? So suppose we have y equal to +1, y equal to -1. This is 55% probability, this is 45% probability. If I use a loss function of 0, 0, 1, 1, if that's my loss function, which one should I predict? Should I predict y equal to 1 or -1? If the loss function is just 1, 1, 0, 0. 0, 1 loss function. It's very easy. We should pick what? The maximum probability, right? High probability. Now, if our loss function is something like this, where we really care about false positive, we don't want it to have any false positive. Which one should I pick? Which one should I pick? Now, if I pick y -1, do I get any false positive? You will never get any false positive, right? Because you predict to be -1. Now, if I predict to be +1, then I have 45% probability of making a false positive. So, and this is going to cost me very dearly because this is going to be 1,000 loss one, right? So, which one should I predict? I should predict this. Okay. So your prediction depends on what kind of error you want to minimize. That's the story. If in this case the -1 and +1 probably are very close to each other, and if you're really, really worried about false positive, you don't want any situation in which a person is actually -1, but you predict to be +1. You don't want this situation to happen at all. Then in this case, you better predict that person to be -1, not +1. Otherwise, you have a you have a 45% probability of making a very costly mistake. Okay. So in other words, what prediction you make depends again on the loss function you use. In other words, typically, the best prediction should be based on the customer's needs. Okay. So if you are making prediction for a customer, whether the customer is a bank, or the customer is CIA, or the customer is any other supermarket or something, right? If you're making prediction for a customer, the best practice is to use a loss function that they prefer. However, in reality, in most cases, even the customer doesn't really specify a very clear loss function. So in reality, when we do data analysis, the typical most common choice is still to use the 0-1 loss. Okay? That's still the most common choice we use, unless you know very clearly what your goal is or what your preference for the loss function is, right? But that's the principle that I want to say. Okay. Now let's come back to the third case. So I just said that when y equal to, so when y is completely determined by x, then we have y equal to fx. But if y is not completely determined by x, then we have a two-step procedure. The first step procedure is I estimate p y given x. The second step is based on my estimation, I predict y hat based on p hat, right? Those are two steps. And I use different loss function. Here I typically use KL or cross-entropy loss. Here I use the loss function that I want, right? So that's the message here. Now it turns out that's not the only way to do things. Okay? The other way to do things is even if so I have x, I have a y. Again, y is noisy. By noisy, I mean at each x value, there are many different y values possible. So this is one way of doing things when this happens. The other way of doing things is even if y is noisy, okay? Even y is noisy, I am going to, my goal is not, I do not estimate the distribution. I do not estimate the distribution. I still try to find out an f, okay? So even if y is noisy, my goal is still to find an f that helps me to predict y as accurately as possible. Okay? So I will, because even if y is noisy, I can always write the following equation. I can always write y equal to fx plus, now you're very familiar with this. Right? So E means, look, so this is fx. And fx is not really y. Okay, it's not really y anymore. Because y still has many values. But I will just use some E to describe things that I cannot explain. That's basically it. Okay? So y is equal to fx plus E. And my goal is to find out what this f is. Now, this sounds almost exactly like what we did when y is noiseless. But there's a fundamental difference. When y is noiseless, I know there's a true underlying f that link x to y. So y is completely determined by this f. Here, this f is not some pre-existing underlying true relationship. Okay? There's no true mechanism that link x to y in the sense of a function f. Because here y is not determined by x at all. But we are just trying to find out a function ourselves. We're trying to find out a function f that helps us to best predict y. That's all it is. Okay, so that's the key difference between the two. It looks very similar. Actually, it's not the same, right? So my y hat would just be my estimated f. Okay? That's it. So what is this? What should this f be? When y is noisy, what is the best f that can help me predict y? Well, again, that's a question I already asked you in my introduction, which is, if I want the function, the f that best help me predict y, again, first of all, it depends on my loss function. Because here the loss function depends on this e, okay? So L1 is e absolute value, L2 is e square, and then you take expectation. And so if we use L2 loss, again, then this optimal f, again, you are very familiar now, is EY given x, right? So in order to make the best prediction of y, I should try to learn EY given x. And how do I learn EY given x? Same story. I give a hypothesis set, h, consisting of many, many different h, and I pick the h that that basically come closest to EY given x. That's the story. It's exactly the same as before. Okay, so this second approach looks very similar to the noiseless case. The only difference is in the noiseless case, I know that there's an underlying relation between x and y that's described by a function f. Here, there's no such function f, but here I'm going to learn I'm going to learn a function that's my own definition, right? So I'm going to learn EY given x, because y is noisy. So there's no true f, right? But I'm going to learn EY given x, if I'm minimizing L2. That's it. So now my goal is to learn fx equal to EY given x when y is noisy. This function has also a name, which is called a CEF, right? Which is what this is. Conditional expectation function, right? So CF. And that's the function that I want to learn, okay, when y is noisy. And this approach is basically, when y is continuous, then this approach is basically called regression, right? Okay, because what regression is doing is basically trying to learn EY given X. Conditional if we use L2. Okay, that's just. Now, if Y is not continuous, if Y is discrete, like +1, -1, or 0 or 1, then what do I do? Well, in that case, this approach basically looks like this. Let me describe, right? Suppose now Y has two kinds of values. You can think about them as +1, -1, or 0, 1. So I'm writing Y in different colors, okay? So this is one kind of color, this is another kind of color describing different Y values. Here, X is two-dimensional, X1, X2, and we're drawing Y this way. Okay, so remember, now we have two approaches. The first approach is to estimate underlying P first, and then based on our estimation, predict Y. The second approach is directly try to find out a Y hat, which is directly try to find out a function that come very close to EY given X. That's the continuous case. In the discrete case, the analogy is the same. Okay? In the discrete case, we have two approaches. One approach is I estimate the underlying probability of Y equal to 1 versus Y equal to 0. And I'm going to predict every point. I'm going to make a prediction. Suppose this is observed data, but I'm going to make a prediction here. I'm going to say, okay, according to my estimate, at this point, the probability of Y equal to 1 is 0.6. The probability of Y equal to 0 is 0.4. So do I predict Y to be 1 or 0? Depends on my loss function again. If I use 1, 0 loss, I predict Y equal to 1 here. That's one approach. Okay, that's the first approach. The second approach is forget about estimating underlying probability. I do not estimate any probability. Okay? I just want to find a function f that helps me to separate these two. And that's it. Okay? I don't estimate probabilities. I just try to find out, look, what is the best line, right? What is the best function that essentially separate these two data? Y equal to 1 versus 1, 0. If I can find out a function that describes, that goes like this, that separate them, then that's my function. Then I'm just going to predict all the Y values here are 1, all the Y values here are 0. So that's the second approach. So in other words, again, right? So everybody get the idea. The first approach is estimating probability first, and then based on the probability to make a prediction Y. The second approach is directly try to find a function that directly give me a Y hat. Okay, and we have continuous. So I know that this all sounds very abstract to you, but in the following course, I'm going to describe many different algorithms that basically use these two different approaches to do things. Now, when it comes to classification, so this is called a classification. When Y is discrete, it's classification, right? So when it comes to classification, I'm sure everybody has, or I hope, right? I hope everybody has studied logistic regression. Have you? No. I think you should. I mean, I'll describe what logistic regression looks like, and then you'll see what it looks like. But it should be familiar to you. But anyway, so logistic regression will be the first approach. So it estimates the probability first, and given the probability, make a prediction Y. All right. There's another approach called support vector machines (SVM). That it's a machine learning. It's a machine learning algorithm. That's essentially the second approach, which is directly try to find a line that separate them and then make predictions. Forget about estimating probabilities. So we'll cover them, and in fact, these two approaches actually can be unified into a single perspective as well, which we'll talk about next time. All right. So I'm running out of time, but I think I'm finishing my lecture. There's only 2 pages left, so we are finishing this lecture, and starting next week, I'm going to start my first sort of a class on actual method, right? So we'll talk about regression in starting next week. What I want to say now is the time to begin writing your first homework. All right. So I will post a message on the first homework. The first homework is going to be due, I think, 2 weeks from this weekend. So I give you 2 weeks. And again, like I said, the homework basically writing a report on any topic that I have covered in this first lecture. All right. So that's it. If you have questions, let me know. Okay. So let's finish today.